All right. So we've all seen exponential functions before. We've seen them in Algebra 1 and Algebra 2, and here we really go a little bit deeper into them. So basically, exponential functions are power functions. A power is anytime you've got a base and an exponent. So exponential functions are power functions. But the thing is, the base is a constant and the exponent is the variable. So until now, we had things like y equals x cubed and so on. Now, it's something like f of x is equal to 3 to the x. Okay, now the exponent is the variable. It's the x. All right. The big thing about exponential functions is that they all have asymptotes and they increase rapidly. Okay, so for example, if you went to so like at the end of winter break, right, you come to school and everything's fine, and then you haven't seen your friend in like a very, very long time, and you see your friend and they are just incredibly sick, just horrendous looking, right? And you're like, oh my gosh, hi, and you give them a hug, and I missed you so much, blah, 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 blah. And that was 8 o'clock in the morning, and then by 10, you're like, oh, I don't feel so well. By lunch, you're really not feeling well. You go home and you just crash. So what happened? Your friend had some bacteria. You had virtually no bacteria. Virtually no, because we all have a little bit of bacteria inside. But you had virtually no bacteria. But what happened? Your friend hugged you, they coughed, they sneezed, whatever. So some of their bacteria now landed on you. And what happens to that bacteria? It starts multiplying. And within hours, you go from having virtually none to having millions and billions and trillions. That is exponential growth, right? So right here, you went from having virtually no bacteria to a whole lot of bacteria. So within a very short amount of time, you had a huge growth in the population. So what happens? Okay, the first day you're not feeling well, the second day still not feeling well, and your parents decide, okay, it's doctor time. You go to the doctor, they take one look at you, and yep, you're in for it. So what do? They give you antibiotics. You take the antibiotics 1 day, 2 days, and then all of a sudden, you know what? You're feeling a lot better, exponentially better, one would say. So whereas you had a whole bunch of bacteria in your body right after you started taking the antibiotics, you now have none. So just as it increased very slowly, it decreased very quickly. It decreased very quickly as well. All right? So that's the big thing about exponential functions. We'll talk more about this in a little bit. So the general form is this. F of x is a times b to the x. And an example is here. So here's where you have, 4 to the x, 1 over 3 to the x. So you could have, for example, f of x is equal to 2 times 3 to the x, right? So this is a, you have a constant, times b to the x. Here are some more examples of exponential functions. 3 to the x, half to the x. And then here you have e to the x minus 1. And we all know, just like 1 and 2 and 3 and 4.5 are numbers, so is e and pi, right? And we'll talk more about e later. All right, so here's what exponential growth and decay look like. All right, so the function is f of x is equal to b to the x. So for example, you have f of x is equal to 2 to the x. Now, are there any values of x that would make that function undefined? Can you think of any? Can you plug in a negative number into x? Yeah, 2 to the negative 2, that works. Can you plug in 0? Sure. Can you plug in a positive number? Sure. So you're free to plug in whatever you want into x. X can have any value. That's very, very important. So for all exponential functions, I mean all of them, the domain is always all real, always. Okay? No. Well, okay. So now let's look at the y. So suppose you have 2 to the x. And if x is a very large number, like 2 to the 1,000, how big is y? Large or small? Very large. So then when we go small, so when x is 0, how big is y? 1. 2 to the 0, it's 1. When x gets even smaller, so -1. So when x is -1, so now you have 2 to the -1, how much is y? 1/2. All right? Still positive, but a small positive number. So when x is, I don't know, when x is -100. So this is 1 over 2 to the 100. How much is that? Is it positive or negative, first of all? Positive, but a big number or a small number? A very small number. So the numbers are getting smaller and smaller and smaller, but never reaching 0, never into the negatives. So the range, it's not important for me that you memorize it, but you understand it, right? As the exponents get smaller into the negatives, the values get smaller, but never reaching 0. So the range is always, for the default, b to the x, 0 to infinity. Okay? And that could move up or down, but for now, that's what it is. Okay. All right. So, end behavior, right? As x approaches infinity, y, the limit approaches infinity. And as x approaches -infinity, where does the y value approach? As x approaches -infinity, y approaches 0. Okay? All right. Exponential decay, same situation. Again, domain is all reals. We'll talk about what the function looks like. The range is the same. So they're pretty much the same, but take a look visually of what exponential growth and decay look like. Exponential growth, this is like the amount of bacteria in your body. They're growing, okay? So as x gets large, y is moving away from 0. This is how I want my students to figure this out. So as x gets large, y moves away from 0. Here, the bacteria in exponential decay are decaying. So I use the words, it decays to 0. So as x gets large, y gets close to 0. Y decays to 0. All right? Here, as x gets large, y decays to 0. Okay? So yes. Yeah, just kidding. Okay? All right. I love exponential functions. Like it's so exciting. I love. I love everything. I do. But like, I'm telling you, Precalc, my favorite thing to teach. It is.
What's your favorite math?
So, there's so much of it that I love. Like calculus, love calculus. Right? Huh? Well, you know, like they're both so fun to teach. Yeah. Okay. They're different. That's the thing. Okay. But then linear algebra afterwards. Oh my gosh. So much fun. That's what you do in college. Oh my God. Like I could take like 5 more classes on linear algebra and like I wouldn't mind at all. Oh no. Okay.
It's like hard algebra?
No. It's like matrices and all that good stuff.
I don't know what that is.
Linear algebra. It's college material. Way up. And then differential equations, like, oh my gosh, like there is so much out there, like so much out there. Okay, let's get back to the task at hand. A function, right, b to the x, an exponential function, is exponential growth if b is greater than 1. So if b, what's b? B is the number that's being raised to the exponent. If that's greater than 1, it's exponential growth. Now, if it's exponential decay, if b is between 0 and 1, so a fraction between 0 and 1, all right? So take a look at these. Classify them as exponential growth or decay. So a, 2 to the x. I just look at this number that's being raised to the exponent. If it's greater than 1, it's growth. So what do you think about b? It's 0.5 to the x. What do you think? Decay. What about c? Decay. What about d? Ah. So a 50-50 chance. Okay, so who says growth? Who says decay? Why would it be growth? Yeah. Because it's a negative exponent. Yes, it's 1/4, but it's a negative exponent. What happens with negative exponents? You flip it and it becomes a positive exponent. So really, it's growth. Yeah, it's a tricky one. So now, how about f of x equals 3 times 1/2 to the x?
Wait, say it again.
3 times 1/2 to the x.
That's decay. Growth.
Okay.
That is decay.
It's decay. It gets slowly smaller and
So you have to look at the number that's being raised to the exponent. The number that's being raised to the exponent is this. It's less than 1, so it's decay. Okay? So the standard form of the function is a times b to the x. So there can be a constant here, a. It's b that you look at. It's the number that's being raised to the exponent. So if b is greater than 1, it's growth. All right. We're going to be graphing, and no, we're not using calculators. Okay? All right. So describe the asymptote, domain, range, and all that good stuff. Okay, so we have 2 to the x. The asymptote for these default functions where there is no vertical shift, and in this case there is none, the asymptote is always y equals 0. Okay? Always. Unless there's a shift. Yeah, then it shifts. Yep. Okay. Y-intercept is pretty much f of 0, right? And that's 2 to the 0, so it's 1. Okay. Now, to graph, I like to put in a couple of points. Now, exponential functions, like we said, get very large very quickly. You always want 0 because that's a critical point. You always want, when you pick points, to be equal opportunity when you pick them. So you want positives, you want negatives, and you definitely want 0. For exponential functions, it's always up to you what you want to pick for x. I found that when it's exponential growth, -1, 0, 1, 2 are a good choice because, like I said, once you get into x equals 3, the numbers get super large. Okay, so this is always a good choice. I end up always picking these for exponential growth. So here we have 2 to the -1, which is 1 over 2 to the +1. So that's just 1/2. Here, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. Okay? As long as it fits on the grid from -10 to 10, let's say, go ahead and pick these 4 points. And then when we get into like the 32s and so on, then it gets a little, then we don't have to do that many. Okay. Okay. So here, all right, when x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2, and then 2, 4. Okay, we must show the asymptote. Again, when I'm grading and when I do the points, there is always a point at least awarded for asymptote. And now, here is something that will give you little to no credit. Okay? That right there. That, my 5-year-old does that when he's doing connect the dots. That's not what we're doing. An exponential function does two things. It has an asymptote, so you have to show me that it follows the asymptote here, and it grows very, very quickly, so you have to show that. All right? Okay, so the domain, what's the domain of exponential functions? Always all reals. The range is 0 to infinity. And behavior, as x approaches negative infinity, f of x is, the limit is 0 and infinity, and it's continuous on its entire domain. Okay? Huh? Continuous, remember we did continuity. It's basically like if there are any gaps or breaks. Right. Okay, so let's do one more. Here we have 3 to the negative x, right? So the asymptote, again, is y equals 0. Y-intercept, f of 0 is what? 1. Still 1. Is this growth or decay? It's decay. Why is it decay? Because 3 to the negative x is really 1 over 3 to the x, which another way of writing it is 1 over 3 to the x. So it's really growth. I'm sorry, it's really decay. And you don't have to go through all those once you learn to recognize it right off the bat. Now, for decay, again, because numbers get so large and so small very quickly, I choose similar numbers but shift it over 1. So from negative 2 to 1. This is not a rule or a law of the land. It's just my preference based on experience. You get nice and cute little values with those, okay? So 3 to the negative 2 is 3 squared, 9. And then here we get 3 to the negative 1, 3. 3 to the 0. 3 to the negative 1, we get 1/3. So at negative, okay, so my asymptote is here. And I'm at 9, 3, 1 over. 3, 1, and 1/3. Okay. Domain, it's an exponential function, so it's all reals. That's a freebie. Range, same. This time, though, as we approach negative infinity, the limit, infinity, and then this is 0. And it's continuous on its entire domain. Okay. So now, transformations are the same when it comes to exponential functions as they were, for rational functions and polynomials and all that good stuff. So let's take a look a little bit. Look at this one. 2 to the x, the blue is the original function. Okay. Now look at what we have here. You have 2 to the x plus 1. You have a plus 1 added to the x value. That shifts the graph left by 1 unit, right? So what you do is you take that x plus 1, set it equal to 0, x equals negative 1, so it moves to the left by 1 unit. So it's the same transformation, okay? When you do that, does the asymptote shift up or down? No. Okay. Take a look at this one. 2 to the x versus 2 to the negative x. It's a reflection around the y-axis. So basically what happens is the blue growth or decay? Growth. Is the red growth or decay? So you see how growth changed into decay when we did that. Okay? Here, look at what happens. You have 2 to the x, and then it's multiplied by a negative number. The negative reflects it around the x-axis. Okay? All right, natural base. Let's move on. So same transformations are going to apply. All right, so let's talk about natural base. Most real-world applications that involve exponentials have a e inside. So what changes, like compound interest, how something loses or gains in value, right? Like property, or a car would lose value, or a property would gain value, right? All of these things are applications of this. So they all involve this irrational number e called natural base. Okay? And so here's where it comes from. This term here, 1 plus 1 over x to the x, so 1 plus 1 over n to the n, or 1 plus 1 over x to the x, this is a term that it shows up very, very commonly in a lot of math and physics equations and formulas. So lots of times, you know, you're working away. When you get to upper level math or physics, you're working away, and then all of a sudden things reduce and you have that term come up, 1 plus 1 over n to the n. And a lot of times the situation asks you to see what happens as n or x gets very, very large. Okay? So a lot of times we have to look at what is the limit as x approaches infinity of that very common term. So you know what I'm going to do for a minute is I'm going to graph that here. Okay? Let's see. All right, so here's the graphed version, right? So that's what I'm graphing, 1 plus 1 over x to the power of x. And I want to see what happens as x approaches infinity. So let's graph this. Yeah, so that's what you get. So I'm not concerned about with the left side. I'm concerned here with the right side. So you know what? Let's change our windows for a second. So let's do 4 window settings, and I want to go from 0 to like 1,000. Enter. Right? Do you see what happens? What happens as x approaches infinity? It levels off, right? And it levels off. At what value would you say it levels off? Well, let's see. Let's do menu. Here's one thing I like to do. Trace. Enter. In trace mode, you can plug in any number and it gives you the value. So when it's 500, when x is 500, y is 2.72. What if when x is 750? Oh, 2.72. What if when x is 999? Oh, 2.72. And actually, if I increased the number of digits here, this levels off at 2.71819, which is what? What value is that? It's E. Okay, it levels off at E. So that's the magical thing about this. So if you go here, whoops. So if you go here, and if you have e to the power of 1, how much is it? 2.71828. So 2.72, that's where it levels off. So this term here, okay, the limit as x approaches infinity is a constant value. And it's given the symbol E. Anybody know? So now you know where E comes from. Anybody know why it's called E and not F or G or H? It's named after a mathematician named Euler. That's how the name is spelled. It's not Euler, that's Euler. He was not Dutch. German, maybe? Around there. He's Euler. So okay, fun fact about, trivia fact about Euler. If you're ever on Jeopardy, okay? He's responsible for coming up with so many different things. So they kept calling things like Euler's formula, Euler's number, Euler's method, Euler's theorem, Euler's blah, blah, blah. So they realized that everything was going to be called Euler's blah, blah, blah. So they stopped calling things. So when he came up with things, they stopped giving it his name. And instead, they started giving them the name of the second person who came up with it independently. Just so not everything in the world would be named Euler's blah, blah, blah. So that's a little bit, again, if you're ever on Jeopardy and that comes up, you need to give me on-air credit. So as x approaches infinity, the value comes exceedingly close to this. So that's how we label that as E. Okay. Next. All right. So here we're going to graph e to the x. Okay. E to the x. This is the same as 2 to the x or 3 to the x, except it's now 2.71828 to the x. So the asymptote is still y equals 0. The y-intercept, f of 0, is still 1. This is exponential growth, so I still choose those same 4 digits. And so here I have e to the minus 1. Now, for these, you will use your calculator. For the e's, for graphing with e, you will use your calculator. So this is going to be 0.37. E to the 0 is still 1. E to the 1 is 2.7. E squared, 7.4. And by the time we're done with this chapter, you will just know that E squared is 7.4. So here we have an asymptote again. And e to the minus 1 is there. E to the 0. E to the 1. E to the 2. Okay, again, this is one of my examples where I say we're not sending anybody to the moon with this graph. So 2.7, close enough. Okay, just make it somewhere 2.5 and or 2 and 3. All right. NASA's not going to take this and send somebody to the moon with it. Okay, so there we go. That's e to the x. Okay. When you take Calc BC or Calculus 2 when you're in college, come back and I have a very funny joke with e to the x. But you have to take Calc 2 before. So come back. All right. The domain is negative to positive infinity. The range, same. This is getting old now. Same here. It goes 0 on the left, infinity on the right. And it's still continuous everywhere.
Just like basically, E is almost 3.
It's almost, yeah, it's 2. Yeah. Exponential functions are not very, they're not very, what do you call it? Like, they're not very dramatic. They pretty much follow in line with, yeah, they're very predictable. Okay. All right, so now finally we have a shift. What does that do to the graph? Moves it up 3 units. Okay? So now, if the graph moves up 3 units, everything about the graph moves up 3 units, including the asymptote. So the asymptote here is going to be y equals 3. This is how the asymptote changes. All right? Now, y-intercept is f of 0, and it's going to be e to the 0 plus 3,
4.
which is 4. Okay? So here, it's going to be e to the negative 2 plus 3. What is e to the negative 2? But there is a 2 here. So this should say plus 3 actually. Right? So I don't have the values here, but e to the Here, e to the 0 plus 3 is 4. E to the 1, I'm sorry, this is e to the 2 plus 3. So it's 7.4 plus 3, 10.4 here, right? So look, once you get to 10.4, don't continue for another point because it's going to be way too big to graph.
5.7.
Where? But what is this one? What is can somebody tell me what e to the negative 2 plus 3 is? No, e to the negative 2. Here, this one. Can somebody, huh? 3.1, thank you. Okay, so now when I graph this, the asymptote is at 3. The last one, okay, so because here I already hit 10.4, this is going to be way too big and it's going to go off the grid, so I'm going to eliminate it. And you can do the same, okay? This is what I was talking about before. So here I have 3.1, 4, and then 10.4 is like way up there, so this is going to look like this. It goes up very, very quickly. Okay? All right. What's the domain here? Negative to positive infinity. And what's the range?
Negative 3 to infinity.
3 to infinity. Now, could we have figured that out before graphing? Yeah, how? The asymptote. Okay, so the asymptote is at 3. And we know that this is a positive function, so it's going to be above. So it's just 3 to above, to infinity. And then as x approaches negative infinity, the limit is what? 3. And as x approaches positive infinity, it's infinity. And it's continuous?
Negative infinity.
Everywhere. Good. All right. Okay, how many of you have seen this formula before? You should all have seen it. Everybody has seen it. So this is the, you've just forgotten that you've seen it. This is the compound interest formula, okay? So basically, if you have money invested in an account, and it's compounded n times a year. Compounded n times a year means you're paid n times a year, right? Right, so basically what I'm saying is, like, compounded n times a year. So if it's compounded 4 times a year, it means the bank calculates and pays you interest 4 times a year. That's what I mean. Okay? And yes, when it's compound, the word compounded is what tells you that it's added to the previous balance. Okay? So let's take a look here. What does P stand for? Yeah, that's the principal that you go to the bank with. All right, that's your initial amount. No, they're both the same. L-E. Okay. It does. Okay, so R is the rate, and you know you have to put it as a decimal. Okay. And then N is the number of times you're paid in the year. T is the time in years. All right. All right. So this person, right. Okay, so this person invested $2,000 into an educational account for her daughter when she was an infant, and I'm assuming she means the daughter. The account has a 5% interest rate. If she does not make any other deposits or withdrawals, what will be the account balance after 18 years if the interest is compounded quarterly? All right. So The $2,000, that's your P, that's your principal. Okay? Now, the 5%, that's your rate, 0.05. And then, the balance after 18 years, T is equal to 18. And, okay, N is equal to 4, right? Why is N equal to 4 here? Because it's quarterly. You're getting paid 4 times. So now, A is equal to P, 1 plus R over N to the power of NT, 2,000, 1 plus 0.05 over 4, 4 times 18. Obviously, this is a calculator one. Okay? All right. So A has to be $4,891.84. Okay. For these, I don't specify that you need to round to 2 decimal places. But it's money, and it's pre-calc honors. And if you don't round to the proper place properly, then I do take points off. All right? All right. Now, yeah. Okay. So, if continuous, or let's do this one too. Continuous interest. So this one, the bank is paying you 4 times a year. But what if the bank was paying you an infinite number of times a year, every single millisecond, every single nanosecond? If the bank was paying you interest, then how many times in the year would that amount to? Infinity. So then, if I take that formula, if I take this, and now, if n is infinity, right? So what happens as n approaches infinity? What does this look like that we just, what does that look like? 1 plus something over n to the power of n. Look, here, 1 plus something over n to the power of n. Do you see that? It's practically the same. 1 plus 1 over n to the power of n. What happens as that approaches, as n approaches infinity? That turns into e. So now that becomes e to the RT. How the r goes from here to here, that's upper level math. All right, but that's the
just because R is
Purdy
infinity,
formula.
Right? Like,
R is not, R is right. R is not
Oh,
infinite.
N
N is infinite. Okay, so now she goes shopping, this lady, and she finds an account that pays 5% interest, compounded continuously. When you hear the word continuously, you use the E formula.
does that ever happen in real life? Do people like do talk?
Yeah.
Gives you more than.
So let's see how, well, let's see how much, yeah, it should give you more, right? Because here you are getting paid 4 times a year. Now you're going to be getting paid an infinite amount per year. She is making so much money with this account, like so much more money with this account. So let's see. Let's see when her investment will triple. Okay, so look at what it says. When will her investment triple? That means if I have A equals PE to the RT, what's P? 2,000. What's A? 6,000. And then the rest is the same. So 6,000 equals 2,000. E to the, right, Gabe? 0.05 T. Okay? All right, let's divide this. We're going to use some algebra here. Some stuff from algebra. So 3 equals e to the 0.05 t. How does that work? How do we solve this? Okay, yeah, so we take the ln of both sides. All right, I'm relying on your algebra 2 knowledge here. So ln of 3 is 0.05 t.
Your ln of e.
Ln of 3. T is ln of 3 over 0.05, which is 22 years. Put it in the calculator.
What was the ln of 3? The ln of 3 will be that? Like the first step? You substituted the e for
Yeah.
ln. That's it.
So, yeah, so I had 3 equals e to the something. The way you solve it is you take the ln of both sides. So ln, ln.
Oh, okay.
Now, ln of 3, whenever you have ln and e together, they go away.
Oh, right.
Yeah.
Why is it not an L? Like, I've never understood that.
Huh?
Isn't it the natural law?
Okay, so that's another,
It's the log of
no, that's another Jeopardy question. That's another Jeopardy one.
Do you know?
It's ln, so natural log, it should be NL, but the reason why it's ln is because it's in French, and in French it's logarithme naturel. Yeah. I don't speak French. I mean, I used to speak fluently. I speak fluently,
What language?
but anything related to math trivia, I got them. Yeah. Have I told you why slope is M and not S? No, I did. Look at you, Mutare.
What?
Mutare.
The new one is, You have to pronounce it correctly. You have to spell it.
Euler. We don't own. Okay, so in addition to investments, what else follows exponential growth? Well, populations of people, animals, bacteria, amounts of radioactive material. So, take a look. We have the 2 varieties, right? Exponential growth and decay. So this one, okay, another thing about this book, nobody uses this N business, okay? In the real world, it's Y, not N. Okay, so here we have N equals N sub 0, 1 plus R to the T. Sub 0 means it's not, it's the initial, right? In actuality, in the real world, it would be Y equals Y naught, 1 plus R to the T, but we're not going to make too big of a deal with this. Right. So you use this if something is growing a fixed amount per year, let's say, right? So like your rent increases by $200 every year, you use this, okay? Population increases by 20% every year, you use this.
You wouldn't use this for bacteria, right? Because it doesn't.
Okay, so listen.
Sorry.
When the word continuous is used, whether it's population or your car or your value of the house or whatever, when you hear the word or read the word continuous, this is the one you use. And real people say Y equals Y naught e to the kt. Now, it's R in this one, K in this one. R and K are both rate. Okay? If it's growth, we say positive R or K. If it's decay, we say negative R or K. A state's population is declining 2.6% annually. Okay? Not continuous, annually. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population in 15 years. All right. I'm just going to use my Y's. I'm going to ignore that the book likes their N's. All right? I prefer Y, but if you want to do N, it's fine. Okay. Just be consistent. Okay, so Y naught, the initial value, is 11 million. We don't put zeros. Like it's too many. It's too much writing. Okay. R, because it's decreasing, is negative 2.6%, which is negative 0.026. T is 15. So now this is going to be y equals y naught. So it's y naught 1 plus r to the t, right? Y equals 11, 1 minus 0.026 to the power of 15. Can somebody plug this in the calculator for me, please?
7.4.
7.4. 7.4. So do you just say 7.4 million people? Okay.